Oh, you can see my screen, correct?
Yes, sir.
Okay, so I have a rough schedule. This is the timetable for the various topics and the order in which I plan to do. I don't have dates yet. I will fill in the dates. Yes, and so what we have done so far, we have introduced, the motivation for the course, what the course is about and some of its requirements, and then been started in the last few classes talking about modeling, okay? How to model the system, because it's one of the three main components that is involved in doing formal verification and particularly model checking. So we are looking at how to model software and hardware examples using the formalism of transition systems, and specifically defining those transition systems using symbolic logic. We did a first order logic recap, including quantified Boolean, the use of quantified Boolean formulas to compactly represent both transition system and its behaviors. So we were talking about how to model concurrent systems, which we will complete today. That is, that we will finish. And there is a concept of fairness there that I will informally introduce. After that, today you will see some Z3. You've already seen some a quick demo of Z3, because the first assignment for you will be in using Z3. So Diganta will be introducing its Python interface, where you could write a program in which you call a SAT solver as a procedure. Okay, so far you've seen how to use a SAT solver, and you will see one more example today using a GUI interface, okay, in an interactive mode. But there is another mode in which you will have to use Z3 solvers if you want to build model checkers using SAT solvers, wherein you use its programming language interface in a particular language to call the solver as a sub process. And after that, based on the modeling so far that you've seen and informal introduction to what model checking is, I'm going to, in the next class, introduce to you this symbolic model checker called new SMV. Okay. Now you see demo of some examples, that you still have not seen a formal introduction to the specification language, which is temporal logic, and also the techniques, how exactly you do the algorithms for model checking. But I want to introduce this the tool informally, so that you can start modeling systems in that tool, and also do some simulation, symbolic simulation, as well as some model checking, even before we actually see the formal introduction of the specification language. Okay, because that you can do start using model checker as a black box before you know how exactly it works. That will be the topic of the next lecture, an informal demo of new SMB. And I expect to give out assignment 1, which will be problems on Z3, on use of Z3 and new SMB. after that. After that, you will see where we will introduce you formally to the temporal logics as property specification language and so on. So I will upload this, with some dates also here to Moodle, and we will go through this as we go along in more detail, this timetable. So I just wanted to give you the initial part. So where were we? Okay. Yeah, this is where we were. Yeah, see, the meaning, okay, the co-begin, co-end, the exact semantics is not exactly captured by here. I will show you that is described in the book, and I will show you in a moment. But let's, for the moment, use this composition mechanism as I've shown here, okay? So asynchronous composition involves taking a disjunction of the transition system for each, disjunction of the transition relation for each of the subsystem. So in such a way that you will march exactly one of them, okay? You can arbitrarily pick one process and choose to advance one step of that process while keeping all the other processes idle, okay? And yeah, so all the variables corresponding to other process, including the PC for that process, will remain the same. And that's how this thing was composed. So you start with, for a moment, ignore the co-begin. I mean, just informally, what I'm saying is co-begin spawns these two processes, and by initializing the locations of each of these processes to its entry point, okay? And there is an initial state which determines the initial values of all the shared variables, okay? And then the transition relation of the asynchronous composition of these two things is just the disjunction of the transition relation corresponding to these two processes, okay? When you do that, what you have is something like what you see here, okay? So as I said, the state, the universe of state, is the cross product of the it's a cross product which has the local component, the local state for each of the processes, and one copy of the global the shared state. So that's how the state was defined, as you could see here, okay? The state S here consists of all the local components for each of the processes and one copy of the shared component, and that's how it is defined. So given that, then the effect of these taking this disjunction like this setting of the thing is equivalent to setting. So here, what is the state? The local component, the shared component, is the turn variable, and the local component is just there are no variables, just the PC. Okay. So to begin with, you have the shared variable initialized. In this case, it can take an arbitrary value, either 0 or 1. And after execution of the co-begin, what you have is both the processes get the PC of them gets initialized to L0 and to their respective entry points. Okay, so you can either start with turn is equal to 0, turn is equal to 1, and after you execute the co-begin, co-end, the two processes respond, and then the individual the PCs are set to their respective entry points, which in this case is L0 and L1. After that, you take one transition, so you interleave the transition, okay, for each of them. So you can either pick, so you can pick one arbitrarily one process to advance, okay, and that's how that you do. So here, this transition corresponds to advancing process 1 from its entry location L1 to the location corresponding to where the non-critical location, okay, NC location, and this is the flip of side of that, okay, and so on. So so I hope you had some time to review this. Are there any questions about the way that I've constructed? Are you convinced that what is shown here graphically is the transitions system corresponding to this, taking this disjunction? Any questions there? So let me ask you a specific question. Why is there, see, there's a non-deterministic transition from this state to either this one or this one? Why is that? Amin?
Hello.
Yeah.
Can you hear me?
Yes.
So could you repeat it once?
Yeah. Why is there a non-deterministic? Whenever there is two possible transitions from the same state, I call that as being non-deterministic. Correct? So I'm asking you,
yes,
what are two non-deterministic transitions from that state? What do those two transitions correspond to?
So like we have given disjunctions, right? So in a step, only one of the clause can be executed.
Yeah. Okay. So that's
so
right. Yeah.
Here at least maybe L1 can go to NC1 or like L0 can go to NC0.
Correct. So now, then we see now two non-deterministic transitions. Okay, one a self loop here, and another one corresponding to this. So Paramalai, why are there? What are those two transitions? Why is there a self loop? What does that self loop mean?
The self loop means it is executing the wait instruction.
Correct. Okay. So because process 0 so when does process 0? So it waits for turn is equal to 0. Okay. Okay. So here, this transition on the right side, I'm sorry, the transition on the right side here corresponds to, so no, but why exactly is there a self loop here?
Because process 1 needs to wait, right? So because turn equal to 0, so process 1 needs to wait.
Correct. Process one needs to, yeah, no, but process one needs to wait. I understand. So, but from here, since turn is equal to 0, only process 0 can advance. Okay. So that corresponds to L0 going to, I mean, NC 0. Okay. So from NC 1, yeah. So here you could, yeah, this corresponds to the case where, here it is, so, okay, you have chosen L1 and that gets to NC1. And yeah, so you're right that this corresponds, the self-loop corresponds to the process 1. If you chose process 1 is not enabled here because process 1 has to wait, correct? If you choose process 1, if you choose to try to advance, because then there is a wait instruction there. Therefore, if the scheduler chooses process 1, it won't be able to advance it, correct? Because it is waiting on turn is equal to 1, but turn is equal to 0 here, and therefore it it busy waits here. So this corresponds, the self loop corresponds to the scenario where you are choosing, you are trying to advance process 1. Okay, the scheduler chooses process 1 to advance, but it cannot advance. Why? Because it is waiting for turn is equal to 1. You see, that's why there is a self loop here. Okay, so this self loop corresponds to, do you understand what I'm saying? See, the reason is this self loop corresponds to the case, although you know that only process 0 can advance here, correct? Because if the scheduler chooses process 1, it cannot go from NC1 to, it has to wait at NC1, okay? But this loop, this self loop corresponds to the case where the scheduler ends up ignoring process 0 forever. Why? Because we have chosen to completely abstract the scheduler, and we have done it in a non-deterministic way. You can either choose process 0 or process 1. So if the scheduler happens to keep on ignoring process 0 and chooses only process 1, then you will be stuck here forever. Correct? Is that clear? Why?
Yes.
Yeah. So it is a result of it's a result of this abstracting the schedule non-deterministically by choosing, we arbitrarily choose one of these processes, okay, in our interleaving. So the effect of that, using non-determinism to abstract the scheduler, is that you could, you end up having a situation where a process which cannot make progress because of these, because of the wait, is being chosen, okay, to advance. So the one that is that can make progress is being ignored indefinitely. Okay, that's what is happening here. Similarly, that is the case here too. Of course, you can always choose. There is also a transition which you can choose. Okay, but if you look at that, because we're completely abstracted the scheduler and say we can arbitrarily choose any of the process, therefore you end up including, in this case, behaviors wherein the it is possible that you indefinitely ignore a particular process. In this case, and at this point, this happens to be the case where that is the only process that can actually make progress, because when turn is equal to 0 and process 1 is at NC1, it can never advance. It will wait there forever, because the only way turn can become 1 is by letting process 0 to advance. Okay, that is what is happening. Okay, this you could say it is unrealistic. Okay, in practice, the schedulers never ignore, okay, forever a process that is enabled, that can make progress. But since we have chosen to ignore, to abstract away the scheduler, we are getting this this behavior. Similarly, you have a self loop here, you see. So here, after choosing benevolently to advance process 0 to NC0, once again, the self loop corresponds to the case, Ratnakar, where corresponds to the case where, to which scenario? Wherein?
The scheduler is on, even though the turn is saying 0, the scheduler is only trying to schedule process 1.
Process 1, okay? So that is the effect of this completely abstracting this thing. See, you want to keep as little in your modeling as possible, and therefore non-determinism is a good way to do it. No matter which schedule I use, I want to be able to prove. Okay, but as a result, what is happening? So there are two things I started out informally. Yes.
Could you repeat what you said? You want to keep as little what as possible?
No. In modeling, you want to throw away. Okay. So since we wanted to prove, what we wanted to ensure was, usually that is the case in concurrent programs. We usually want to analyze the combined behavior of these composed systems, regardless of what the actual schedule, actual schedule, the way that these processes are scheduled. Therefore, that's why we were motivated to abstract away the scheduler. And one way to do was choose and say, oh, I could choose any one of these processes arbitrarily. Okay, that is how we used non-determinism, by making non-deterministic transitions here, by saying, oh, I could interleave in such a way that I could pick any one of the process. But as a result, okay, so that is good in terms of abstracting. So I'm trying to show you some not so desirable effect of throwing away that detail. So let me draw your attention. So given this, that we have thrown away, we have abstracted the scheduler completely by using this non-determinism, wherein you say, I allow the next transition to be picked arbitrarily between any one of the process, even if that means that you are allowing for the scheduling of the process which cannot make any progress. As a result, what's happening? Okay, so I mean, let's take this model. So now this model, last time we observed that it indeed preserves the safety operation, the safety property, correct? The fact that on all feasible paths in every state, it is not the case that you can have both processes at the same location, at the critical location, CR0 and CR1. Okay, that is true for this, right? Why is that true? I'm claiming that the safety property, so read G here as that in every state, on every path that is originating from an initial state, it is not the case that you can be in a state in which both processes are in their respective critical section. That is, PC0 can be CR0 and CR1. Why is that true?
Like because of the turn variable.
Yeah, no.
Actually, in the graphical representation, it is not there. So
yeah, it is not there because if you see it, there will be bubbles, but you will see that transition is not even possible. Okay, by construction, because here the way that I'm constructing these transitions is, how do I construct this graphical representation of the transition, a graphical representation of the transition system? By enumerating all the states, okay, which is the cross product. So some of the states are missing. So CR0, CR1, okay, where both locations there are certain bubbles missing, just like in the while loop program, you had some bubbles missing. And there will be transitions from there. One exercise that you could do in this case is for you to complete this transition system, okay? I strongly encourage you to do. You add those things, okay? Because the transition relation is defined in a left total way, you will have transitions from those states. CR0, where the PCs of our PC0 is CR0 and PC1 is CR1. But when you try to complete all the transitions, you will see that those states in which PC0 is CR0 and PC1 is CR1 will be unreachable from these initial paths starting from initial states. Okay, so if you try doing that, and then the transition relation, the way a single component relation doesn't allow you to do that. And like Ratnakar observed, it is true that it is because the way that the weight statements are designed based on turn being 0 with one process and turn 1, those will not be reachable. Okay, and the way that you can actually prove them is actually checking if indeed that state in which PC0 is CR0 and PC1 is CR1 is never reachable. Okay, so that is how you ensure that indeed it is not. One way of ensuring is to construct explicitly this transition system as a graph, and then check it out that those bad states are unreachable. Okay, now that is one way to do. Obviously, that is not a practical way, because then the number of states could be too much. Okay, but there are that is one way to do. That is called explicit model checking, and there are tools to do it. Whereas in symbolic model checking, like new SMV, what we do is represent the transition system as formulas, and we have algorithms to manipulate formulas to check what the reachable states are, and then check if indeed, and ensure that those bad states, which in this case is both being in the critical section, are not reachable. Okay, that is how you do. And you see, the first exercise that we will do with new SMV is verifying this mutex. Okay, so I hope you are convinced that the safety property is preserved, and the way that you have to convince yourself, I suggest at this point, when you go after the lecture, is for you to draw the complete transition diagram for this example based on this transition relation, combined transition relation that I've defined, and convince yourself that these bad states are kind of completely removed from this part of the thing, that they are not, there's no transition, sequence of transitions from these initial states to those bad states. Okay, that is an informal exercise for you, and that's the reason this thing. Now I ask you the question, is starvation freedom this property that eventually every process gets to reach its critical location? Is that true? That's what F here means, that on every path, starting from the initial state, eventually you will, each process will get to its critical section. Is that true here, Paramalai?
No, sir, because
Why is it not true?
because we saw the self loops. The
Correct.
scheduler might pick the wrong.
Yeah,
process.
no. Yeah. So our scheduler, since we have abstracted the scheduler away, we are allowing for the hi. Let's welcome Diganta. Hi, Diganta. Diganta, your mic is muted. So I just was welcoming you. So say hi to the rest of the folks.
Hi.
Okay. So yeah, just give me 5 minutes and I will, then I will have you, yeah? Take over, correct? Yeah. So what is the time now? So when I have this in full mode, I don't even know the time.
4.
So it is
It's 4.
Okay. Yeah, so give me 5 minutes and then I'll hand it over to you, Diganta.
Yeah, sure.
Yeah, so it is true. So it's the reason that the starvation freedom is not is because of this thing. See, and that is happening because we kind of, you could say, we over abstracted the scheduler. It's never the case that so when you use non-determinism to abstract the scheduler in this way while modeling concurrent systems, this is kind of the undesirable effect, okay? That because in reality, in real life, schedulers will never ignore, okay, an enabled process forever, okay? Because that is not a fair schedule. It'll usually give each process a fair chance, okay? Therefore, what I'm getting to is if you abstract the scheduler this way, then such progress properties you may never be able to prove because there'll always be some paths in the in your transition system in which violates this progress property, like this liveness. Therefore, yeah, so the system is safe, but it is not starvation free for the reason Paramalai observed. So what is the, but if you throw away the scheduler, which we want to do from the point of view of keeping the complexity, to handle, the reason for throwing away scheduler or abstracting the scheduler is to keep the size of the system under check. So then the way that you do is you introduce the notion of fair paths, okay? So, and then restrict your checking of these properties only to a subset of the paths which are fair. And this, the reason that this thing is happening is because of the use of non-determinism to throw away the abstraction, in the process of using non-determinism to abstract the scheduler, you are kind of making the model too imprecise, okay? And which means that, so that is the effect of that. And therefore, that is handled by saying, okay, this introducing notion of fairness constraints, okay? And the way that is introduced is by checking, yeah, I mean, all this is, we will formalize later on. Now, right now, when you see in new SMV, these concepts you will see there. And so I'm giving you like a teaser introduction to these concepts, when you do things with new SMV as a black box. Okay. So fair path in a model, a path in a model is called fair if along the path certain events must occur infinitely many times. And the events are captured by certain predicates over the state being holding good. So your Kripke model, in addition to the labeling function, also has what are called fairness conditions. These are conditions on the state, okay? And a path is considered fair if that event characterized by that condition happens infinitely often, okay? So in this case, for example, you could say our fairness constraint is in every state and enable, those paths, a path is considered fair only if in every state on that path, an enabled transition of a process is never ignored forever. Or another way of putting it is enabled transition corresponding to a process making progress must happen infinitely often. Okay, therefore, these paths with these self loops here are not fair. Okay, so and that is and that's how you do. Okay, so you specify, you model it by using non-determinism. Okay, as much as you want, and then you get around this undesirable effect by putting in defining, by specifying fairness conditions to make the model checking process to be restricted to only a set of finite paths. Okay, so this is just a teaser introduction. Okay, so I'll get to this later on because I want to give Diganta an opportunity to do. Diganta, so how, okay, so I'm going to make you a co-host. Okay.
So,
yeah, but what I want to do is, see, guys, I know that Ratnakar, you joined a little bit late. I had a very brief demo of set 3. It's interactive thing. Ratnakar, you haven't seen that, have you?
I haven't, but I don't mind. You can continue.
Yeah, but how about the other ones? Okay, so Diganta, I don't know how you have planned it. You're going to directly introduce Python interface, or you want to show some examples. I want you to do. So I thought that you could start by doing the that example that I showed you. Or I could just simply show one small example using the interface, or you could do that yourself before you move to showing the Python interface. How do you have it planned?
So I originally had it planned that I'm going to directly go into the Python interface and start with a small example there. But I think I can show that same example on the riseforfun.com web interfaces. And
okay, so if you do that, then that will be good. I don't mind even if you go towards, hey guys, next week, see, we lost one class last week, okay? I want to have a makeup class next week, okay, for that. So would, our regular classes is on Wednesday and then Friday. Wednesday at 11:50 and Friday at 3:30. Would it be okay to have the extra class on Monday at 11:50 for you guys? I mean, for everybody, I'm saying. Because
Monday, I think
actually we have a class.
machine learning class on 11:50.
at 11:50 you have a class. Okay. No. Okay. So let's not get into that. Okay. So we can have that extra thing even later on. So rather than wasting time. So if you can't finish your demo today, Diganta, you can continue on Wednesday. But for Wednesday, I'm also planning new SMB. So let's see how we go. Okay. So go ahead. I have made you a co-host, and you can.
I'll start sharing the screen. So can people see my screen?
Yeah, maybe. Yeah, I can see it.
Yes. Yes.
Yeah. Also, is my voice and everything clear?
Yeah.
Yeah, you're audible. So this is actually quite a good web interface for a lot of things. It also has a Z3 interface among those things. So Z3 itself, as you may know, that it is a SMT solver, right? So it takes in SMT expressions and then it produces models or produces unsat depending on. For those of you, SMT stands for satisfiability modulo theory. So SAT solvers are decision procedures for deciding satisfiability in propositional logic. Like I had mentioned earlier, you can extend this satisfiability to logics which have multi-sorted logics. Okay, so when Diganta says it's an SMT solver, what he means is that you can have they are able to solve the satisfiability problem of formulas over where the variables range over other types like integer, reals, and so on. Okay, go ahead.
Yeah. So I think what I'll do right now is basically go over a little example involving some integer variables over here, and then we're going to look at the same example using Python code, right? Okay, I will talk about how to install Z3 and all of that on your system. So this web interface you can just access via this link here. I can send this later on to the chat or through Moodle.
Yeah, I'm assuming that after the int example, you also will have some examples.
Yeah.
Okay, go ahead. Yeah.
I won't show that in this. I won't type this into the. I won't type the transition system into this. But I'll just directly show it in the Python code.
Good enough. Yeah.
So there is a specific language for SMT solvers. Like all SMT solvers accept inputs in this particular format, which is, I think it's called SMTlib2 format. So this is some code that is already written by default there. I'm just gonna erase most of this because this is not really, like, we don't need to worry about all of these kind of things, right? So the first thing that we'll do is declare some constants. Now, constants in SMTlib2 and in Z3 are actually considered to be functions that take no arguments and put out some particular thing of a particular argument. So for example, if we go back to their definition, see, so it says declare function, the name of the function is X, it takes no arguments and it outputs an int. So this is sort of the syntax, if you will, for a constant, because a constant is a function which takes no arguments in. And so I'm going to just keep those things, and let's look at this first assessment.
So here I just want to interject. So I mean, a constant, like he said, it's an arbitrary constant. So it's almost like a variable. Okay.
Yes.
Constant which can take any value is as good as technically like a variable.
Yeah. In fact, I think calling these variables would probably be like a less confusing name. So I'm just going to go ahead and call them variables. But Z3 does have like this technical thing that it is actually a constant, and there is nothing called a variable in Z3. So so in that sense, these are constants. And
I think there is a function called declare const, no?
Yes, which is, I think, a shorthand for this.
Shorthand for this, yeah. Okay.
So so these X, Y, and Z, I'm going to okay, so for now I'm going to call them variables, but later on I'm going to make a distinction because I don't want to confuse Python variables versus Z3 variables, right? And we'll see that later. So, so we have X, Y, and Z, which are variables, let's say, and now we have some assert statement of this. So what this is saying is basically assert is saying that this should hold true, and it's saying that, okay, they should be greater than equal to, okay, so what is greater than equal to what? This expression is greater than equal to this expression. So what this expression is saying is, okay, multiply 2 and x. And what this expression is saying is add y and z. So what this is essentially saying is, if I write a comment over here, is that 2 times x should be greater than equal to y plus z, right? Does that make sense to everyone? So this is just the syntax for this is just that these operators are written in the beginning and then you write the argument. So you have multiply of 2 and x, add of y and z, and then you take those two things and say, okay, greater than equal to of these two things. Does this make sense?
Yes.
Yes.
So now we have 2 more commands that we are passing to Z3 here. One of them is saying check set. So check set is going to take all the asserts that you have passed in before this, and is going to tell you whether there is any values of the particular constants that you have chosen, this x, y, and z, whether they can take any values so that this is satisfied, right? So if I click this right arrow, it will actually do the check set. And the next thing is get model. So get model, okay, I'm going to maybe comment this out and let's first see what check set just gives us, right? So it's going to run and it's going to take some time, and now it gives us sat. So sat means satisfiable. So yeah, of course there is some values of x, y, and z for which 2 times x is greater than equal to y and z, y plus z holds, right? I mean, you can easily think of a lot of integers for which something simple like this should hold. So let's see what Z3 gives us when we do get model. So what get model will do is basically if check sat succeeded, that is if check sat returned a sat, then what get model would do is that it will give us values for x, y, and z that actually satisfy all the asserts that we have placed. So again, if I run this, see it says sat, and now it returns this model. So this model says that, okay, x, this is some complicated way of just saying x is a constant of type int, and its value is 0, z's value is also 0, y's value is also 0. So what Z3 is saying that, yeah, this is satisfiable, and an example for this satisfiability, or a witness, if you will, for the satisfiability is when all of x, y, and z, all 3 are just 0, right? Because 2 times 0 is greater than equal to 0 plus 0. So if I change this to greater than, let's say, then, okay, sorry, mistype there, sorry. Yeah, so if it changes to greater than, like strict inequality instead of greater than equal to, then if I run this, it will probably not give 0 for, yeah. So now it says that, okay, 2 times x is greater than equal to y plus z, where y is minus 1 and z is 0, right? So it decides to put minus 1 in place of y instead of just 0, right? So maybe we also want to say that, okay, x, y, z are all positive variables, right? So let's assert that. And let's say, okay, greater than, and what's greater than what? So we have 0 is greater than, let's put in a bracket here. So 0 is greater than x, right? So this should make sure that x is always greater than 0. And when we run this again, we should see that. Oh, sorry, I think I missed it.
I think you should have it the other way, no? Greater than.
I mean, yeah, I could have say
This what you just now said was that x is less than 0.
Oh, sorry, yeah. I'm sorry. Yeah. This is bracketing is out. So why is it? Okay, so
Yeah, you should not have those brackets, correct.
yeah, I
I
think
think there's an extra closing bracket.
Yeah, there might have been, but I think
No,
it's
no,
fine.
correct.
No, no, so you're right.
Yeah. Yeah, okay, so yeah, so x is now greater than 0, and that forces x, the output of x, to be 1, right? So let's copy this and say that, okay, y and z are all greater than 0, let's see. So y and z, and now when we run this, it should make sure that, yeah, so x is now 3 and y and z is 2. 2 and 2 and 2 plus 2 is 4, so 2 times 3 is 6, and all of this is fine. Now let's also say that, okay, we'll say that x is actually less than y, right? So let's see what happens then. So x is less than y, right? Yeah, so now it says that, okay, x is 3, y is 4, and z is 1. So that's fine, right? 1 plus 4 is 5, and 2 times 3 is 6. Now, of course, if you also say that, okay, x is less than z as well, then, you know, we should get something like unsat, right? Yeah, it says unsat. And now it gives me an error because model is not available. Of course, if it is unsat, then it makes no sense to ask for it for a model from him, right? Because there is no model that you can get. Like, there are no values of x, y, and z for which all of these constraints go. So this is essentially basic idea of how Z3 operates. So like this particular format of specifying constraints is called the SMT-lib2 format, and there are multiple such SMT solvers other than Z3 as well, and all of them actually accept this particular standardized format. And so this particular website, this riseforfun.com, allows you to write in constraints in this format to Z3, and it will check for whether it's sat or unsat and give you whether or not the model is available, and so on. So let's look at what the general workflow is for working with Z3, right? So first thing is that you declare some constants or variables or whatever you want to call them, basically. So you declare x, y, and z, and you say that, okay, all your constraints will be based on these. Then you assert some constraints, right? And then you finally, what you do is you do check sat and then get model. So there are some problems with working with just this pure SMT-lib2 format. For example, there is no if then else, like, this is not a programming language per se, right? So you can't say that, okay, if it is satisfiable, then do this, or otherwise don't do this. So if you wanted to get rid of this error message, for example, you would have to know whether checksat returns a model or not, right? Because you want to print out a model if it does, and if you don't want to like call get model if it does not, whether if it returns unsat, right? So you need some sort of if then else statement, but SMT-lib2 doesn't have it. We will also see other examples, other situations where just specifying constraints in SMT-lib2 is kind of too restrictive. So this is why most SMT solvers also provide some sort of language bindings, and we'll look at the Python language binding for Z3. Right? So
by the way, guys, so are you all familiar with Python? Are you comfortable programming in Python? The three of you?
Yeah, I'm okay with it.
Yeah.
I did try a little bit of Z3 in Python.
Okay, so you are okay with Python. Anyway, so Diganta will introduce Python, but of course Z3 also has similar interfaces with other
in other languages
too. So
I can actually I can go over to the this Git page for Z3. You can see. So there are C and C++ bindings, which are actually always there by default, and there is Java, OCaml, Python, and Julia, and also there's WebAssembly, and yeah. So if I mean, of these languages, I am very familiar with Python and C++. So I have only used the Python's bindings for Z3 myself, but if you want to go over C++ or C bindings, then I can maybe take a look, and we can go over that together if people are interested, and if there is things that can be done. So we can think about that maybe later on. But yeah, if somebody is confused about some code that I'm writing, just let me know. So, okay, so I'm going to go over to Python right now. Okay, so before that, let me just talk briefly about installing this. So if people have used Python, do you know of pip, like this Python package in manager? So okay, how many of you guys are working on Windows, or how many of you are working on Linux, Unix based things?
I'm on Ubuntu Linux.
Yeah, okay.
Yeah, me too.
Right. So most of you guys are on some Unix based thing, right? So you'll find pip is probably in your for Ubuntu it should be in apt. So that's just apt cache install pip. And once you have installed pip, all you need to do is install this Z3 solver package, right? So it's just this command, like just doing this should get it installed for you. So I wanted to just also show this live, but I mean I have this Z3 already installed on my system. So I thought I'll be able to get a Ubuntu virtual machine running, but I couldn't. So yeah, so just do this and it should install Z3 for you. But even after that, if you have some problems, let me know via mail or through the Moodle messages, and I'll look into what your problems are. Okay. So yeah, so let me go over the Python interface. So firstly, okay, font sizes is the font size okay?
I mean, I guess I'm old, so I need bigger.
Yeah. I'll make it slightly bigger. I think
Slightly bigger, yeah.
Is
Yeah,
this fine? Yeah.
it's okay.
Can everyone see? A
Yeah.
few yeses. Yeah. Okay. Oh. Yes. The first things like that you want to do is basically import Z3. Now, so let's go over this particular example that we have, right? So we want to define X, Y, and Z first, right? So the way you do that is basically inside this Z3, there are various functions that will allow you to create this particular variable. So for integer type variables, what you do is z3.int, right? And then inside this, you need to pass in a string name for this variable. So I'll go over what that exactly means, but let's just write this code for now. So what we're doing here is basically saying that, okay, this Python variable X refers to a Z3 constant of the name X, which has the type int. Does that make sense?
Yeah.
So similarly, we can, do this again for Y, Z, and okay. So we similarly say that, okay, the Python variable Y refers to the Z3 constant Y. Similarly, Python variable Z refers to the Z3 constant Z. This is why I want to stick with the name like constant, because these objects, this X, Y, and Z are something recognized internally by Z3. And these are different things. These are Python variables, right? So this technical distinction will become important when I show a sort of a corner case that you need to, like a quirk that you need to avoid when you're writing code. So a very quick way to basically just solve for some constraint is to call z3.solve. And then you just pass in all the expressions that you want to solve, right? So for example, let's look at this first assert here, right? So what I can say is inside z3.solve, I'll just pass in 2 times x is greater than y plus z. And so when you're working with Python, you don't need to write this prefix syntax. You can just use your normal Python syntax, and Z3 will automatically create the correct expressions when you say 2 times x is greater than y plus z. And you can just pass this entire expression into Z3.solve. So when we run this, yeah, see, it gives us that original example that we have. Now, suppose we want to add in these other constants, right? So one of the ways we can do this is by just ANDing it with this expression. And for that, we do z3.and. You can't use the Python AND because that Python AND only works for Python Boolean expressions, sadly. So you need to use z3.and, and then you need to pass in 2 expressions. So let's say this is positive. and then it should again, yeah, it's giving me x equal to 1, y equal to 1, z equal to 0. So basically, the workflow over here that we had for asymptotic2 is kind of similar over here, where we are defining the variables. And then here we have this single sort of quick way to call the solver for a set of constraints. So we can also add in other things. Let's say that z is positive, y is positive, right? And then if we do this, yeah, we get this. And then we can also add in these other constraints later on. Now, what I wanna basically sort of make sure you understand in this little example is that these things here, these are some special, like these return some special objects called Z3 expressions, or I think the technical term for it is ASTs. So you can actually pass these around your functions, and this will be like some contain all of the information about the constraint that you need. So when you're saying 2 times x is greater than y plus z, it's not actually calculating 2 times x or y plus z for any particular value of x, y, and z or anything like that. It's not also making any actual comparison. So what it's doing is it's creating a symbolic representation of this particular expression that you have, packaging inside inside some Python object, and then passing it to the Z3, right? And then Z3 will use that, unpack it, and then solve based on that, right? So for example, if I print the type of this, say 2 times x, you'll see that it's not like integer or anything like that. It's something much weirder. Yeah, so it's arithmetic reference, right? And it's basically saying that, okay, it's an expression of type arithmetic. So if I do say 2 times x greater than y, let's say, then again you say, okay, so it's Boolean reference. So it's an expression which has type Boolean, right? So these are basically Python objects of some different type. Essentially, they are not just arithmetic or Boolean types, but they are somehow encoding expressions. Yeah.
So with it is also giving some models. Z is equal to 2, y is equal to 2, x equal to 3. It's just what is that when you, although it's it's arithmetic reference, it is giving some.
Yeah. So that model is coming from this one. This Z3.solve also prints on the model.
It is repeating the same model. That's all.
Yeah. No. Okay. So there is basically there's this first print statement, and now. So if I put a print statement here, let's say,
because it is solving the other one and then it's doing it. Okay.
Yeah. So yeah, if I do this, then it will, I think, be yeah. Yeah. So this is what's happening. So yeah. So now, before I move on to a little bit more of a complicated way to call the solver, which gives you more control of what you want to do, but is a little bit more code, I just want to sort of point out a very potentially annoying quirk of Z3. So let's consider this. So we have 2 integer constants, p and q, let's say, right? Now what we do is Z3.solve, let's say, p not equal to q. Right, and of course this should be stat and it should give us a model, right? So okay, let me just remove this previous comment of this previous part so that it doesn't confuse us. Yeah, so it says p is equal to 1, q is equal to 0, and that is a valid model for the constraint that p and q are different. Right, but now suppose we keep this Python variable p and q the same, but we say that, okay, we'll pass in the same Z3 constant named p to both of these Z3.int calls. Now see what happens. Yeah, it says no solution. So essentially, this is why I was making the distinction between the Z3 constants and Python variables. So essentially, this situation is that p and q are both Python variables referring to the same Z3 constant, which has the name p. So this is why when you do p not equal to q, you're essentially asking Z3.solve to solve for p not equal to p internally. So, and that's why it gives you no solution. So does this make sense to everyone? What's happening here and why we're getting some behavior that might seem counterintuitive or unexpected?
Yeah, it's okay.
Yeah, okay. So my advice is basically just keep very like track what your Z3's constant names are very carefully. Like don't reuse names, because then you can, like, unless you specifically want to, because then you can end up with situations like this, right? So yeah. So now let's go back to this example that we had, and we are now going to basically do the same thing, but we're going to try and get more control over the actual solution process. So instead of calling Z3.solve, Z3.solve is actually a shorthand for a more complicated sort of setup. So if you remember what we're doing here, one of the things that we saw is that the checksat and get model are two different calls, right? So Z3.solve actually does a checksat and then get model, and if there is no satisfiability, then it prints no solution. It handles all of that on its own, but we can also handle that ourselves, and that gives us more control. So to do that, what we need to do is basically create a Z3 solver. So we can say S, or let's say solve is equal to Z3.solver. What this does is it creates a solver instance. So this is like one instance of a Z3 interactive session that you have going on. And you can pass various constraints to this solver instance and then ask this solver instance to check for satisfiability. And you can then try to get a model from this solver instance and so on. So to get sort of the same kind of a behavior as we had before, what we now have to do is add in constraints to this solver, right? So we say solve.add, and here we put in some constraints. So so as before, let's try 2 times x is equal to y plus z, or greater than y plus z. So 2 times x greater than y plus z.
This app will change your life.
Yeah, I couldn't hear you. Hello? Hello? Is someone
No,
something?
sorry. No, I.
Okay. So when we just add something in the solver, as you can see, when we try to print, nothing happens really. Because we've just added this constraint to the solver, we're not actually checking anything or printing anything. So what we instead want to do is we want to actually check for the satisfiability. So let's do this in a new paragraph. Solve.check, and this function will actually check whether the constraints that are currently added inside the solver are sat or not. And if they're sat, they will return a particular sat instance or otherwise an unsat instance. So for example, if I have r equal to some r or ret equal to solve.check, then what we can do is print ret and see what it is. Right? Yeah, solve.check returns sat, and that makes sense. So let's now add more constraints, right? So now we can add more constraints slowly. Solve.add, let's say x is greater than 0, y is greater than 0, z is greater than 0. Let's add in all of those things. And again, now if we run this, it returns sat. Now, whenever it returns sat, the next thing that you can do is actually call get model, right? So you can say m equals solve.get solve.model, right? So what this will do is basically it will return a model that satisfies. Okay, so when I say model, I mean a set of assignments for all your constants such that all the constraints are satisfied, right? So it will return that, and now we can print this model again, and so solve.model return m, right? Yeah, and okay, so this window may be blocking this. Yeah, so as we can see, it returns sat and it says z equals to y equals to x equals 3, as we had seen before. Now again, we can keep adding more constraints until we get like an unsat situation. So let's say x is less than y. So then we can, yeah, so it goes to a situation where z is 1, y is 4, x is 3. Now, if we say that x is also less than z, then we have the previous situation as before. Yeah, so it says unsat. So this is the first print statement, and then we have a huge error because we have some Z3 expression here. Model is not available, which is basically analogous to this error here, right? Model is not available. Now we can avoid this in this case because now we are actually inside a programming language and we can check if whatever we return from solve.check is actually sat or unchecked. So we can say if ret equal to z3.sat. So this is not some Python Boolean true or false. There are basically some constants defined inside Z3 called sat and unsat, and you can use that to check this. So then we can check whether it's Z3.sat, and if only it's with sat, we try to print the model. Otherwise, we say not calling solve.model equals unsat. Right. So now if we do this, see it says not calling solve.model because unsat. And of course, if we say comment out this first line, then it's going to actually return the same thing. So this is again a very simple demonstration of why it's actually better to work inside of some programming language bindings than just directly in SMTP2, because here you can actually interact with this in a much more fine-grained way. Now, so the next thing that I want to do after this is sort of go into more details about like modeling a more complicated example. Let's say, so I model this example that Sir had. Let me just bring up that PDF. Yeah. So you talked about this today in the class, right, sir?
Yeah, no, they have seen this example, not today, but in the one of the earlier classes.
Right, nice. Yeah. So now what we are basically going to try and do is try and model this as a function inside Z3, right? Or let's say a constraint inside Z3. I'm not going to call it a function because it's not technically a function because it doesn't take something and return something. So again, let me just, okay, so is up till now everything more or less clear? Because do stop me if something is unclear. So it's clear up till now, right?
Yes.
Yeah.
Yes.
But technically, you can define functions in Z3.
Yeah, you can.
So, but that you can do here also, no? So, or can you not? I mean,
yes, you can. But the only functions that you can define in Z3 are uninterpreted functions. So you can't say something like, okay, this is a function that takes in.
No, that's not true. That's not true.
Yeah, I mean, okay. So what I'm saying is essentially that you can define an uninterpreted function, then define a constraint on that function that says, okay, this function returns true only under such conditions, right? So for example, for this, you can say that, okay, T is an uninterpreted function over x0, x1, y0, y1.
I know. That's actually, no, there's a def func.
Yeah.
So where you can directly define this to be taking bool, and bool.
Right. And if I recall correctly, I think at least definitely in the Python interface, because I just checked some time ago. But
okay, go ahead. I mean, I
yeah.
will let you go.
Yeah, but I'll just say what's happening there. So it's like there inside the def bool thing, it will define an uninterpreted function. Like it will basically declare T to be an uninterpreted function. And then you're assigning some extra constraint to say that, okay, T is true only in this particular case. I think that's how that works.
Okay, fine.
I'm not, okay, I'll check as well.
Yeah.
Yeah, so yeah, as before, I think I'll define x0, x1, y0, y1. So, yeah. So again, if you want to define a Boolean, then the syntax for this is like z3.bool is the constructor that you want to go for. This is x0, let's say. And then you have x1. Then you have y0 and 1. Right? And now what we're going to do is again create a solver. So this solver method actually can take a number of different arguments and like a number of sort of advanced knobs that you can tweak as to what this solver does, and that can lead to some optimizations in performance and all of that. And I think you can maybe go through the documentation if you are interested for that. So now let's actually define a constraint that is saying that, okay, let's call the output of this function T. So let's say T tz3 is another Boolean, and this represents the output of this function. And what we're going to say is that we're going to define a constraint that says, okay, t is this expression, right? So we're going to say that t underscore z3 is equal to, now if you look at this, x0 is equal to x1, this is again this is equivalence, which is actually captured by an equality, and that is being ANDed with this dot of y1. So outermost thing is AND, so we need to say z3 dot AND, and then what inside that we have two things. First is y0 equals x1, so y0 z3 equals x1 z3. So it's again equality. Sorry. Yeah, and that is ANDed with not of y1, right? So z3 dot not y1 z3. Right? So this is your AND, and then this is the solver dot add. So this constraint basically captures the fact that t underscore z3 should have the corresponding value for whatever value of x0, x1, y0, y1 we have chosen. Now let's say that, okay, let's fix some initial state, right? So let's fix some initial state that says, say, x0 and x1 are, say x0 is 0 and x1 is 1, right? Or x1 is 0 and x0 is 1. Yes, it's going to. So we add some initial state, let's say. So this represents some initial state that we are adding, like some state that we want to take the transition from. x0 z3 is 1, let's say, and we're going to say x1 z3 is 0. And now, as before, we'll check.
Just one logistics thing. I think the class formally ends at 3:45 and 4:45. Okay, or even earlier. But is it okay for you him to go till 5 o'clock today for you guys? Oh, so there is some chat here. Let's see what.
Oh, okay, sorry, I was looking at.
Paramala has asked a question.
Oh, I'm sorry.
What's an uninterpreted function?
Yeah.
Yeah, I think we went on a tangent. Okay, they're a little bit. Okay, like. Yeah, so I guess Paramala has answered it. No, but that's not true. But
yeah, so I think I can. Should I go over like what I mean there, or?
No, let's defer this, okay? Because that's not important for the thing at hand.
Right.
We will explain, okay? So what the thing is. So you have only like less than, about 10 minutes. Okay, firstly, is it okay from your constraints for the three of you? Even if one of you answers no, we will have to stop here. Okay, for Diganta to go till 5.
For me, it's okay. I'm not sure about
I'm too
others.
okay with it.
Okay, and Amin? Zamin?
Yeah, I was the one who said it was okay.
Okay, so fine.
I think Ratnagar didn't.
Yeah,
Okay.
it's fine for me too.
Okay, good, thanks. Yeah, so 5 is a hard stop.
Yeah. So I have 10 minutes now. So, right, so solver check we do as we did before, and so we have some return from that. And again, as before, we do if red equals z3.sat, then print. I'm just going to directly write solver model. Take the model out or anything like that for now. So now if you run this, okay. So
Something went wrong.
yeah, something has gone wrong. So it is true false equal to in line 12. Oh, right. It's not 0 or 1. It should be
1 and
true
0 is
yeah. 0 and 1 is like integer. So it should be so true and false, like the Python true and false. Yeah. Right. So you can't, I mean, of course you can't use 1 and 0. I don't know why I said that. Like it's maybe because I was talking and saying 1 and 0. So it's what you want to say is true and false because these are Boolean, right? So yeah. So now it says that, okay, yeah. So x1 is false, y1 is false, x0 is true, and y0 is true, and t is true. So okay, we actually haven't set t to be true, right? So what we want to say is that we are taking a transition. So we want to say that the output of this transition function should be true, right? So in some sense, we want to also add this particular constant, solve.add t underscore z3 should itself be true, which is actually a roundabout and redundant thing of saying that, okay, this entire thing should hold, which I think is what we're going to do. So I'm going to just delete this and say, right? And that makes sense, right? Because we're saying that the transition relation should hold. We're just saying this relation should hold, right? Doesn't it makes sense, right? It's okay for everyone?
Yeah.
Yeah. Okay. Yeah. Sorry about this roundabout way of saying this, and yeah, of course, it still gives us the same result, but now, yeah. So I have not written this right. So now, yeah, now there is no t that we need to worry about. So it says that, okay, x1 is false, x0 is true, and then what you get in the end of it is y1 is false and y0 is also false, right? So now suppose what we want to do is we want to start with all the states, like Sarah says here, we want to start with all the states where x0 is 1. And what we want to say is that, okay, x0 is 1 and t of this holds true, and we want to print out all of the models for which this is true. So one of the ways of printing out all of the models for which a certain set of constraints holds true is basically just checking if it is satisfiable, and from that you get a model, and then taking things inside that model and then eliminating that as a possibility, right? So we're going to write a loop to do that. So what we're going to say is,
but the important thing is Z3, or for that matter, any SAT or SMT solver, SAT solver, it does not automatically give out all the satisfying instances. Okay, firstly, having such a feature would be impractical. I mean, there could be so many instances, satisfying instances, and therefore it lets it to the user to kind of do that, pick the model in a user-controlled way. Okay, so there's no feature, you won't find in any SAT solver something like, say, oh, give me all the satisfying instances. Okay, just too many. Okay, so but if you want, you can do it yourself in a controlled fashion. Okay, so, and that's what he's going to illustrate as an example.
Yeah. In fact, like if you're dealing with just Boolean things, there are at least finitely many such models. But if you're dealing with integer expressions or something like that, there can even be infinitely many such satisfying instances, right? So so you want to be sort of careful when you're enumerating through all of these things in general. But yeah, so here I think it'll be, since this like just 4 variables, at the most there can be 16 many things that we're going to print out. So we're going to just print out all of these possible things that satisfies this particular constraint, right? So I'm going to remove this constraint from here. So I'm going to only say that, okay, x0 is true. So x0 is true. That's one constraint that we have, and the t constraint, right? So which is this one here. So given these 2 constraints, let's write a loop. So let me just comment out this part of the code. Let's write a loop to sort of figure out all of the satisfying instances of this constraint. So we are going to do this by basically doing solve.check first in the head of the loop, and we're going to loop until we get an unsat. That is, we're going to loop while we're getting a sat. So while solve.check is sat, we're going to keep looping. Then inside the loop, what we're going to do is the first thing that we're going to do is get the model that we are returning, right? So we say solve.model. And this we know won't give an error because we have already checked that the result is sat. Now, now what we want to do is basically get all of the variables from inside the model. So for example, in this model, we had y0 is false, y1 is false, x1 is false, x0 is true, right? And what we want to do is we want to eliminate this as a possibility for the next return. So we want to say, okay, existing constraints and y0 is false, y1 is false, x1 is false, x0 is true. This particular assignment should not be allowed. So what we'll do is so we will firstly print out the model, and then we'll add this particular constraint into the solver. Add, and we're going to say m dot, so we're basically going to say and z3 dot not, z3 dot and inside that what we're going to do is m dot evaluate, right? And inside m dot evaluate, we are going to pass in these particular variable that we want to like. And so m dot evaluate, what it does is essentially, given a model, it will evaluate a particular expression under the model. So essentially, if you give any expression here involving these variables, it will evaluate and return the actual value of that expression in terms of whatever the assignments of these variables are in this model, right? So in this case, we're going to just pass those single variables in. So x0, z3, let's say. And okay, so we are going to also pass in this thing, which is called, if I remember correctly, this was, so evaluate has this particular flag, which is called model completion. So if you set model completion to true, what it will do is basically, so sometimes what happens is that a particular variable can take arbitrary value, like it can take whatever value. So whatever value a particular variable takes, your constraints are satisfied. So Z3 then does not actually assign a particular value to that variable. So if you set model completion to true, then when you in the evaluate function, then that particular variable, this variable, even if this variable does not have a value in the model, Z3 will still pick some arbitrary value and return over here in this evaluate function instead of returning none. So then what we're going to say is that, okay, this value of x0 z3 inside our current model is equal to x0 z3. Yeah. Okay. And so this says that, okay, x0 z3 has the same value as whatever value the model just returned. So then over here we're going to repeat this for x1 z3 and so on. So for example, and then y1 z3, let's say.
Basically, you're saying they cannot be the same because there is a not.
Yeah. Yeah. So
something different than this model is what you're saying.
Right. So essentially what we're saying is, for example, if our model was this, we're saying, okay, inside this model, y0 had false, y1 had false, x1 had false, x0 had true. So we're saying, okay, whatever inside this model, whatever the value of x0 was, if that is equal to x0, and whatever the value of x1 was, if that is equal to x1, and whatever the value of y0 was, if that is equal to x2, and whatever the value of y1 was, if that is equal to y1, if all of those hold, there's an and here, then we're noting this. So we're saying that, okay, all of these cannot hold together, right? So it cannot be that the value of x0 is the same as whatever you had in your previous model. The value of x1 is also the same as whatever you had in your previous model. Y0 is also the same as whatever you had in your previous model. And y1 is also the same as whatever you had in your previous model. So this cannot hold anymore, right? So we are essentially adding this extra constraint into the solver, which says that, okay, this particular variable should not hold anymore. Like this particular set of assignments should not hold anymore.
Yeah, this is, in simple terms, this is called blocking a model. Okay, so you're blocking an existing model. So,
right. Now, if we run this, so it gives me this basically two things here. So it gives me that, okay, x1 is false, true, or true, true, and depending upon that, y0 is false, false, or true, false, right? So in this way, you can sort of enumerate the number of all the satisfying instances of a particular given model, and you can sort of print them out all directly. So I have, okay, I don't have any time at all, but okay, so I'm just going to do this just one small thing. So I'm going to print out the details of the solver, like at the head. So for example, over here, I'm going to say print solver and solve, just to show that, okay, these constraints are getting added in and all of that. So if I do this, so initially you see the solver has just the t constraint and x equals true, and then you have this model, and then the solver has t constraint x equals to true and the constraint that is blocking this particular one, and then you get another model, And of course, after that, the solver gives unsat. So we're not actually going to print out the final version of the solver. And yeah, so this is the idea. So I have to stop right now. So are there any questions? I'm sorry if like I'm asking for questions at the very last moment, but yeah, is this all very clear? Or is there some confusion?
Yeah, it's clear.
Yeah, I think what we okay. So you will continue. You see, the sequence is this. The planned sequence is this. Is the following. Okay.
Yeah.
So we will finish the Z3 demo. You will continue, and then whatever that you want to discuss, and then we'll start the new SMB thing. Diganta, I'll talk to you offline separately later, maybe Monday, about what I've planned for new SMB, and that I'd like you to help me with, and we will continue with that thing. Yeah, because the next assignment will be guys on both new SMB problems on new SMB and Z3. Therefore, you will have to get familiar with these two. I mean, you have to pay attention to the demos. And I've already uploaded. Okay, Diganta, you upload the document, corresponding, related to Z3 Python interface, how to install and so on. If indeed you want to, upload any links and so on. I've already uploaded, guys, the link for new SMB, how to, and that has all the information about how to download and install and so on. They have released the latest version. Now, I don't know which version you used, Diganta, in the class. Now they have a, some version 6 or something like that. So,
I don't remember. I don't remember which version I had.
Yeah, but in any case, those details will do. And there is a manual, there's a documentation, there's a tutorial, and so on and so on. So since we're meeting only on Wednesday, I encourage you to, first, I want you to have both Z3 as well as new SME installed. And if you have any issues, shoot an email. And also go through the tutorial document for new SME. Some few sections, okay? I mean, the first section, 2 sections, and so on. It has a lot more, but anyway, so at least have it installed, okay? And then if you have any issues, so that then when you're giving the demo, maybe on the next demo, you could follow some of those things, yeah? Okay. So I'll see you Wednesday at 11:50. That's okay with you, correct, Diganta? On
Wednesday 11:50.
Okay, next class is on 11:50. Thank you very much.
So, okay, can I just ask something really quickly before? Yeah. So, is there anyone who's not on Ubuntu? Then I'll just give some packaged installation for Ubuntu. Anyone not on Ubuntu?
Only 3 people are there in the class.
So I mean,
yeah,
all 3 are in Ubuntu. So yeah.
Okay, so I'm going to. Okay, so I'm going to. So if you could, let's see. How do I?
Oh right, I need to stop sharing.
Yeah, you need to stop sharing, and then. Okay, good. So then I'm going to stop the.